Hey guys, this is Mr. Gron, 8.8, solving radical equations. So one objective here, it's to solve radical equations. All right, so here's some steps that we can take when we're solving radical equations. So the first thing that we're going to want to do is what is called isolating the radical. And what that basically means is just get one of the square roots by itself on one side. So if it's like square root of x plus 1 or something equals 5, this is okay to solve. But let's say if it was like 2 plus the square root of x plus 1 equals 5, we would want to take this 2 and subtract it from both sides so that it's just the square root on one side and just numbers on the other, if we can. All right, then we want to raise raise both sides to the power that eliminates the radical. So if it's a square root, like this little one that I just made up, we would square both sides. But if it was a cubed root, for example, then we would raise both sides to the power of 3, right? After that, we're going to solve for the variable. That's going to be either a linear equation where we're just getting it to be x equals and a number on the other side, or it could be a quadratic where we're going to end up with possibly a couple of answers. And then we're going to want to check our solution or solutions for extraneous solutions. All right, so our first one here. Solving this one for x. So the first thing I want to do, I want to isolate the square root, right? I want to get this all by itself on the one side. So I got to get rid of that 5. So we'll subtract 5 from both sides, and we get root x plus 1 equals 11. At this point, I can cancel out this square root by squaring both sides. So one thing I can't do, don't try to subtract this 1 yet, because it's not really plus 1. It's the square root of x plus 1. And so you can't really subtract this 1 out of there because it's not really a 1. It's like the square root of something after you've added 1 to it, which makes it not the same as 1. All right, so square both sides, and we get x plus 1 equals 121. Subtract 1 from both sides, and you get x equals 120. Now for this one, it's going to be a good solution, but we are going to want to get into the habit of checking this with the original equation. So if we'll plug 120 in for x, we get this, which if we start to simplify that, 120 plus 1 is 121, and the square root of 121 is 11. And so 5 plus 11 does equal 16, so that's a good solution. All right, next one, if you want to pause the video and try this on your own. So again, we want to isolate the radical, so we're going to add 1 to both sides. And that's going to leave us with the square root of v plus 3 equals 8. Now I can square both sides, and that's going to give me v plus 3 without the square root is equal to 64. And now we'll subtract 3 from both sides, and we get v is equal to 61. Again, we want to check this one just to be sure. 61 plus 3 minus 1 equals 7. That gives us the square root of 64 minus 1 equals 7, and that would simplify to 8 minus 1 equals 7. So that is, again, a good solution. All right, now we've got 2 radicals in this case, so we can't isolate one of them. So the only thing I can do at this point is just to square both sides. So if I square this side, that's going to cancel the square root. Now, one thing we have to keep in mind, you're not just squaring this part, the radical, you're squaring everything on this side. So that means this 3 is getting squared too. So what you're really doing here is you're squaring this entire quantity. So now when you square this side, it gets rid of the square root. It's just 7x plus 2. But when you square this side, squaring this 3 makes it a 9, and then squaring this makes it the quantity 3x minus 2. So notice that I put that in parentheses now, where that 9 is on the outside. So instead of 3 times the square root of this quantity, now it's 9 times that actual quantity. All right, so if I distribute the 9, that's going to give me 27x minus 18. And now I can isolate x. I can solve this. Now I want to move x to one side, all the x's to one side, all the numbers to the other. I'm going to move the 7 over here so that x stays positive. So we'll subtract 7x from both sides. And then at the same time, I'm going to add this 18 to both sides. And what that's going to give me is 20 on the left side and 20x on the right side. Now we can just divide both sides by 20, and we get that x is equal to 1. Now, is this going to work? Let's double check it. Square root of 7 times 1 plus 2. Is that equal to 3 times the square root of 3 times 1 minus 2? So on this side, on the left side, that would be the square root of 9, and this would be 3 times the square root of 1. The square root of 9 is 3, and then 3 times the square root of 1 is 3 times 1. So that one is, again, a good solution. All right, this one, go ahead and pause and try if you want. All right, so this one's pretty straightforward. Technically, we're going to cube both sides, but because there's nothing on the outside of the radical, it doesn't really matter. We could write the 2's next to it and do it technically wrong, and we'd still get the right answer, so kind of a convenient one. All right, all that's going to happen here is it's going to cancel out the cubed root radical, and then pretty similar algebra to the last one. We'll subtract x from both sides. At the same time, we'll add 3 to both sides. So on the left-hand side, we just get 4, and on the right-hand side, we just get x, and so x equals 4. So let's double check that. We get the cubed root of 4 plus 1 equals the cubed root of 2 times 4 minus 3. And so that will equal, if I simplify both of them, cubed root of 5 equals the cubed root of 8 minus 3 is also 5. So that one's a good solution. All right, now we'll get into some ones that have extraneous solutions. So example 3, notice the difference between this one and the first two examples is now it's not just a number on this side, it's x. So when we square both sides, what's going to happen is we're going to come up with a quadratic. So on the left-hand side, the root cancels out and it's 30 minus x. The right-hand side is x squared. Well, now we have a quadratic, so what do we do with that? We set one side equal to 0. We're going to subtract 30 and add x to both sides. So on one side, it's going to be 0. The other side is going to be x squared plus x minus 30, and that's a factorable quadratic. So that's going to give us x plus 6 and x minus 5. And that's going to have solutions, potential solutions, of negative 6 and positive 5. So let's check these. So for negative 6, we'll plug that in. Square root of 30 minus negative 6 equal to negative 6. And that's going to give us the square root of 36 equals negative 6, but the square root of 36, this is the positive square root of 36, and positive 6 does not equal negative 6. So that means that negative 6 is an extraneous solution. 5, we'll check that. So 30 minus 5, the square root of 30 minus 5 equals 5. Let's see if that's right. 30 minus 5 is 25, and the square root of 25, the positive square root of 25 is 5, so that one is good. So 5 is a good solution. Negative 6 is an extraneous solution. All right, try that one. Okay, again, we square both sides, and we get x squared is equal to 42 minus x. And so we can add x to both sides. We can also subtract 42 to both sides, from both sides. And try to keep these in standard form. And make sure that you're not combining unlike terms. So we should get this. Now, two numbers that multiply to negative 42 but add up to 1. That is going to be x plus 7 and x minus 6. And that and that will work. Our solutions there are -7 for the x plus 7 and +6 for the x minus 6. So -7, +6. Let's check our solutions. So -7 equals 42 minus square root of 42 minus -7. That is -7 equals the square root of 49, which is +7. So that one is not equal. So that's extraneous. And then for 6 equals the square root of 42 minus 6. 6 equals the square root of 36. That one's good. So +6 is good, -7 extraneous. All right, last examples. So what do we do with this one? It's rational exponents. This is no different, right? If we raise something to the 1/2 power, that is the same as taking the square root. Right, so these two things are the exact same. We can treat them the same. If you want to rewrite it like that, you certainly can. You don't have to, though. If I square this, if I take a power and raise it to a power, I multiply the exponents. So 1/2 times 2 is equal to 1. Well, this quantity raised to the first power is just 3x plus 10. So 3x plus 10 equals x squared. Now, if we set this quadratic equal to 0, 0 equals x squared minus 3x minus 10, that will factor to a -5 and a +2, which has potential solutions at 5 and -2. So now if we check our solutions, now for checking our solutions, maybe it's easier for us to think about it because we're more used to using radicals rather than raising things to the 1/2 power. So maybe it would be better to do it like this. It truly does not matter, but this is the same thing, and this I feel like is just a more familiar form to look at. All right, so that is going to give us 15 plus 10, and that is 25. Square root of 25 is 5. That one is good. And then -2. 3 times -2 plus 10 equals -2. That's going to give us -6 plus 10. That will reduce to +4. And that would be +2, not -2. So -2 is extraneous. All right, last one. All right, so this one's very similar. We're going to raise to the 3rd power, however. If it's raised to the 1/3 here, we would raise it to the power of 3 to cancel this out, right? It's the cubed root. So if we do this, it would be x minus 5 is equal to 4 cubed is 64. And so we add 5 to both sides, and we get x equals 69. Now, if we plug that in to check, 69 minus 5 raised to the 1/3, or taking the cubed root, does that equal 4? Well, that is 64 raised to the 1/3 power, and that does equal 4. So 4 equals 4, and that's a good solution.